Audio Jungle. Audio Jungle.
All right. A brass bar having cross-sectional area of 1000 square is subjected to axial force as shown in following figure. Find the total elongation of the bar, full stop, modulus of elasticity of brass is equal to 100 giganewton per meter square. This is the question. Now the bar is something like this. You check the figure here. This is the bar, right? And this bar is what connected with multiple load. Multiple section we have. So I will show you the multiple section first. This is, we just say L, M, okay. This is N, and this is what? P. If this bar, if you check, it is connected with multiple load here. It is 50 kilonewton here, 80 kilonewton here, okay. Then again 20 kilonewton here, 10 kilonewton here, okay. Now coming to the dimension, lengthwise 0.6 meter, here it is nothing but 1.0 meter, and here it is nothing but 1 point. This is the bar, okay. This is 0.6 meter. All right. Now this is the bar. For this bar, basically we have to calculate what they said, elongation, the total elongation. They have used the word total elongation. They can say total elongation or total change in length or total deformation. These are the same word they can use. So if you check how many segments we have, LM segment, then MN segment, and then NP segment. For all three segment, we have to calculate the change in length, and then we have to add. Okay. One more thing, as I told you in starting only, if load is tensile load, then change in length change in length will be positive, means there will be increment in length. Okay, and if load is compressive load, if load is compressive load, then change in length will be negative. Okay, that's this you need to remember. And compressive and tensile load already I have discussed you. Okay, so if tensile load is there, then obviously change will increase, change in length will increase, that will be positive. And if compressive load is there, so change in length will be a negative, that means decrement. Just for simple example, suppose this is the bar. So if bar is what subjected with, if this bar is what subjected with this tensile load, this is what tensile load P. So whatever the change in length you will get, delta L, it will be positive increment. That's the mean of it. Similarly, suppose we have bar here, and this bar is what connected with the, this bar is what connected with the compressive load. This is what compressive load P. So whatever the change in length will have here, change in length, that will be negative, means decrement. This is the simple logic we have to use. Why am, because earlier there was only one bar, so there was not problem. But why I'm explaining this compressive and tensile both in one simple a single question? So because this single question we have here, but if you check individually, three bars are connected uh, together. Three bars individual, if you check, it is connected to each other and now becomes the whole one complete bar. And if you break segment wise, so there are three bars. How much? Three bars: LM, MN, and NP. Then now it is connected together, and hence it becomes single bar. Okay, and it is nothing but a brass bar. See here, a brass bar having cross sectional area of 100 mm square. So all section, that cross sectional area, all section cross sectional area is nothing but 100 mm square. This is the area they are talking, area. So area is what? Same for all. Area is same for all. Okay, here also this is the area, this is whole, it is same. They said, having cross sectional area of 100 mm square is subjected to axial force. huh? Axial force is given, but axial force can be two types: compressive or tensile. So axially they have said it is axial force. There is no tangential force, only axial force is there. But in axial force you have to find which one is compressive, which one is tensile. Let's start the problem. Now how to hit this question? Simple. Okay, now one by one segment we have to take. Total three segment we have. So again I will draw this complete, and then I will show you the segments. It will be more clear to you. The single bar, again I can show you here. And if you check this bar, it's 50 kilonewton. Okay, just take your time. Just first problem, if you nicely you hit this, then obviously others problem will also be the similar. So load here, it is given 50 kilonewton. Okay, 50 kilonewton, and it is like this. And here it is given the complete bar, it is given 80 kilonewton. This side it is given 20 kilonewton, and here this side it is given 10 kilonewton. L, M, N, and P. 0.6 meter, 1.0 meter, and 1.2 meter. Okay, now we'll break this segment. How we'll break it? So check, we have to extend such type of problem. We have to solve in this way only. Just extend this. Where are the segment? We just extend this simply. These are the segments like this. Okay. First we are going to check the segment LM. Okay. First we are going to check the segment LM. So now this is the LM segment. Hmm. This is the LM segment. Remember, should not be tapered. The complete straight line only. Now this, because if you draw tapered bar, then meaning will be different. Okay. Anyway, now for this LM, now we'll show the force. See, this direction we have load of 50 kilonewton. It is given. So for the stability point of view, what will be load at this end? What will be the load at this end? If you take separate individual bar, so this is 50 kilonewton, so this will also be 50 kilonewton, because now then only this bar will be stabilized. It will achieve equilibrium condition. Individually I am saying, because this side 50 kilonewton is given, so just opposite will also be 50 kilonewton, just like action and reaction. So this side 50 kilonewton we have, so obviously this side will just opposite and equal value will be there, then only this bar will be stable. That's the mean of it. Now coming to the next bar, which is nothing but Mn. If you draw Mn here, so make a point like this, is the second bar, which is nothing but Mn. Okay. Now if you draw Mn, then see what will be the load here. Simple. At this point M, what is the load acting? 80 kilonewton. In which direction? Towards right. See, in this right direction means towards right, means in this direction. In this direction, what load is what acting? 80 kilonewton. Now if you check this M and this M, both M are same. This both M, this M and this M both are same. Here you have shown 50 kilonewton. Total at point M, what load is what acting? 80 kilonewton total load. So here you have shown in this bar, first bar you have shown 50 kilonewton. So at second bar at the same point M, in the same direction, what should be adding so that it can achieve 80 kilonewton? So 50 kilonewton already you have shown. So rest 30 newton again you will show here. So check 50 plus 30, again it will achieve 80 kilonewton at point M. Now if you see, this 30 kilonewton inward direction, which is compressive load, now is acting in this direction, inward direction, to make it stable, to make it equilibrium bar. The same load will be acting in this way also, then only it will be equilibrium condition, 30 kilonewton. Okay, just like here this was the tensile load. So always remember, equal and opposite force should be act for the equilibrium bar. Okay, for the neutral bar, for the equilibrium bar, equal and opposite load should act, then only it will be stable individually. Okay, so this is Mn bar. Now coming to a third bar, which is nothing but Np. Np. Okay, this is the third bar, Np. Now right. Okay, now check for the Np bar. N is here, so obviously this will be N, and last point is P. Check at point N, what load is what acting? What load is what acting? 20 kilonewton is what acting. 20 kilonewton is what acting towards left. Towards left, how many loads it is acting? 20 kilonewtons. And in this direction, the last direction, last end or end point, you can check what is the load acting. You can see here it is nothing but 10 kilonewton. Okay, here it is nothing but 10 kilonewton. You can show it. If this is 10 kilonewton as acting, so to make it balance, to make it equilibrium, the same equal and opposite load, equal and opposite. will be 10 kilonewton acting here also. Now check the n, cross check. This is the cross check at point n, this and this. If you meet these two n points, which is the same point actually, but you have taken separately. But once you meet this point n to each other, so 30 kilonewton is what acting in this direction. In this direction, how much it is acting? 30 kilonewton. Okay. Just opposite is what acting how much? 10 kilonewton. If you check the resultant of this, so 30 kilonewton in this direction, 10 kilometer just opposite. So what will be the resultant? Resultant will be 30 minus 10, which is 20 kilonewton. And in which direction? The higher load. What is the higher load? 30 kilonewton in this direction. So in this direction. Check this 20 kilonewton is what acting in this direction or not at point n. Yes, it is acting. So this is the cross check. I would suggest the end points you first write the load, like here the end point is L and P. So L end point is what in this direction 50 kilonewton, you make it, then just equal and opposite, just make it opposite. Similarly here at end point P, we have to show first this 10 kilonewton in inward because it is given inward, and then just equal and opposite here also you can show. So both way you have, and then you cross check also. So now your the meeting point like M and M, for this this bar M and this bar M, you can check 50 kilonewton, 30 kilonewton same direction, so it will achieve 80 kilonewton in same direction, right? So it is 80 kilonewton, hence your distribution of the load for both bar, it is correct. That bar is what 1, 2 and 3. And now check 2 and 3 bar are meeting at point N. If you meet 30 kilonewton and 10 kilonewton, so just equal, just opposite force, 30 minus 10, it will be 20, and higher load direction you have to take, so 20 kilonewton, because 30 kilonewton direction is what inward, hence this is also. This is also correct. Overall idea, you got all three segment separately, and now they are asking the change in length. So obviously here, because this is the bar 1, so the total change in length will be delta L1. Here the total change in length, because it is bar 2, so this is the delta L2. Here this is the total change in length is nothing but delta L3, because it's a bar 3. Okay, right. Now this one is clear. I believe that because single bar, how to get the change in length, last class nicely we had discussed. We have to follow that formula, and we have to get the change in length for bar 1. So first bar 1, what is the bar 1? See, this bar, if you check the load here, it is nothing but 50 kilonewton. Here it is nothing but 50 kilonewton. This length is 0.6 meter. And if you check the area of the bar, what is the area of the bar? In the problem itself it was given, it is 100 mm square. Okay, we have to convert into meter square. So this area is nothing but 100 mm. Now we'll find what is the total change in length. Just recall the formula we had derived. Change in length, sorry, not total, it's a change in length. So recall that formula, and we had written that change in length for the bar, change in length. How to get it? Change in length is nothing but delta L. How to get it? I will derive just in short, but you please remember this formula. So what is the formula? We have sigma is equal to Young modulus into strain, epsilon. That is the formula as per Hooke's law. So capital E Young modulus, and strain is nothing but change in length delta L by L. Okay. What is the sigma? Sigma is nothing but load by area, P by A is equal to this Young modulus into delta L by L. So now onward, you always remember change in length. Already I have discussed in previous classes. You check. Now delta L change in length is nothing but PL divided by AE. This will be my formula for the change in length. You always remember. Okay. So in short, here I have derived, but always remember it should be on your tip. Once it comes like change in length, immediately this formula should come in your mind. Remember this change in length. If the load is tensile, then it will be positive. If load is compressive, then this change in length will be negative. So see, this load is what? Tensile load. So directly you can find what is the delta L. Delta L is nothing but PL divided by AE. Now coming to the formula, what is the P? That is load. It is nothing but 50 kilonewton. Keep the value 50 kilonewton. PP into 10 power 3 into uh, L is nothing but original length is 0.6 meter. 0.6 meter divided by that area of the bar is 100 mm square. So just convert 100 into mm. 1 meter is equal to 10 power minus 3. 1 mm is equal to 10 power minus 3 meter. So mm square, hence this value will be 100 mm square, hence this value will be square because it is the millimeter square. Now you just convert into meter square. Into Young modulus is given how much? It is 100 giganewton per meter square. 100 giga Newton meter square. You can write 100. Giga means 10 to power 9. 100 giga Newton per meter square, right? So it becomes 10 to power 9 Newton per meter square. Okay, this will be the value. All right, this is one. Because we have the elongation here, we have the tensile load, hence this value will be, elongation will be positive because it's a tensile load. Now bar 2. Bar 2, we'll write the change in length PL B. See where is the bar 2? This is the bar 2. See, this load is what? Compressive. 30 kilonewton, it is going inward. So it is compressive load. Hence you will put change in length is equal to minus PL by AE. So what is the P? You check for bar 2. What is the P load? 30 kilonewton. So we keep this 30 kilonewton. 30 kilonewton into L. What is the original length for this bar? It is 1 meter. For bar 2, it is 1 meter. So just 1 meter divided by the area AE, 100 10 to power minus 3 square into 100 10 to power 9. Why negative? Because it's a compressive load. Similarly, bar 3 change in length. What will be the change in length? Again, we have to check bar 3 also. It is what? So bar 3, this is also compressive load. See inward direction, it means it is compressive load. Hence minus sign you have to keep. PL by AE. This is the formula, but this is minus. Why it is compressive? What is the load given? 10 kilonewton, I think. 10 kilonewton and length is 1.2. 10 kilonewton into 1.2. So 10 kilonewton means 10 into 10 power 3. Length is 1.2. Denominator must be same. 100 10 power minus 3 square into 100 10 to power 9 because it's a giga, right? Now if you check total change in length for the complete bar, so total change in length for the complete bar, what is that? Delta L. It is delta L1 algebraic sum, delta L2 plus delta L. Plus minus you have to keep. If all three formula, if you check, denominator must be same. So we can write also that this formula also we can write in this way. Hope you will understand this. 1 upon AE in bracket, it is P1 L1 A2 L2. In this way also you can write because AE is common, so you can take. So the formula what we have here, 1 upon 100 10 to power minus 3 whole square means 10 to power minus 6 into, it is 100 into 10 to power 9. 100 into 10 to power 9 and write all the value. P1 L1 P2 L2. Check here, 15 to 10 power 3 into 0.6, 50 10 to power 3 0.6. Next, second bar will be negative P2 L2 will be negative into, that is nothing but 30 into 10 to the power 3. Third is nothing but again it is negative minus 10 into 10 to the power 3, and length is 1.2. 1.2 delta L. If you solve this, calculate each and every steps, so finally you will get approximate, you will get uh, minus of 0. 0
001.
0 0 1 2 meter, which is approximate, you can write 0.12 mm, and that will be with minus sign. It means the total change in length will be decreasing. Okay, it means it is, you can write here, you can write here, you can write here, comment also you can write. Okay, you can write the bar is, the bar is minus sign is what, showing that the bar is now going to shorten, means the length is what decreased actually. Okay, so you can write the bar is shortened, bar is shortened, bar is shortened by 0.12 mm, the whole bar. Okay, all right, all right, so we can have here bar with continuous or continuously continuously varying cross section. Varying cross section, if they are saying varying cross section, that also called varying cross section, means it also called tapered. Okay, it also called tapered section, or tapered bar we can say. Okay, tapered section we can say. So that tapered section, okay, whatever the tapered section we have here, so two types of the tapered section we have, two types of the varying cross section bar we have, two types of varying uh, cross section bar we have. That is nothing but rectangular bar section, rectangular tapered bar section, and second is a circular tapered bar section. So first we are going to discuss here circular tapered bar section. Okay, number one is circular tapered bar section. Okay, circular tapered bar section. Now here in circular tapered bar section, we can say the initial diameter of the bar, because it's a circular, so initial diameter is what, d1, and it is tapering, so it, the area is what varying, obviously cross sectional area is what varying. Now this area becomes, diameter becomes d2, so I can give one reference line. See, this is what reference line here. Okay, now this in diameter become d2, and this in diameter become d1. Okay, the total length of the bar, it was L, and obviously this bar both ends are connected with the load, which is nothing but tensile load. This load can be compressive also. If it is compressive, then change in length will be negative, that's all. Yeah, so load is nothing but P. Okay, what is the load acting? It is nothing but P for this bar. Now whole section, you might understood. If modulus of elasticity for this bar is nothing but E, that is the modulus of elasticity. Modulus of elasticity for this bar is nothing but E. So what are the given value? Given is load P, given is initial diameter D1, final diameter D2, given is length of the bar capital A, given is the modulus of elasticity of bar is capital E. This value will be given to you. You have to find the change in length. Okay, okay, you have to find change in length. For this bar, what they have given, applied load P, applied load P, uh, initial diameter D1, final diameter D2, uh, initial length of the bar is given L, modulus of elasticity of bar is E. What we need to find? We have to find change in length. Means delta L we have to find for the tapered bar. All right, that is our job to find. Now, so what we'll do for this? Simple. If you go for the solution of this problem, so definitely again I'll show you in short. I will draw the diagram, then it will be more clear. Suppose the same bar I have taken here, okay, and for this bar, if you check, load is what acting P here, load is what acting P here. Obviously, diameter, if you check this diameter D1, this diameter is D2, and the initial length of bar is L. Now we start the derivation. Now it's very simple. If I say what is the change in diameter for the complete length L, okay, for the complete length of L, then what will be the change in diameter? I must write the steps. Each step I will write change in diameter. Okay, for length L, for length, for complete length L, what is the change in diameter? You have to say D1 minus D2. I'm talking about the complete length. So for complete length means initial and final point you have to check. So for the complete length L, what is the change in diameter? It is D1 minus D2. That is change in diameter. That is for length L. But what is the unit? What is change in length? What is the change in diameter? What is change in diameter? Change in diameter for unit length. If you talk about for unit length, it is D1 minus D2 divided by L. This is also called rate of, I'll explain you again, rate of change in diameter per unit length. This is meaning per unit length. This is also called like this, which is nothing but D1. Like see, like 10 mangoes in 100 rupees. So one mango or per per mango cost is nothing but 100 by 10. That is the simple concept. So for L length, change in diameter is D1 minus D2. So per unit length, what is the change in diameter? That is D1 minus D2 by L. And that per unit change in per unit length change in diameter is also called rate of change in diameter per unit length. Simple, the meaning will be same. Change in diameter for unit length you can say, or you can say rate of change in diameter per unit length, meaning will be same. So that will be D1 minus D2 by L. All right. Now coming to the next, D1 minus D2 by L. Now anywhere I'll take at any distance x, I'll take the section of this, and this section I can show you by the by this way. I can take, like, this total length is what, L, at any section, and that distance from this section length is nothing but x, this section length is nothing but x, and the strip what I'm considering here, that strip, which is basically, you can say, this thickness, you can say, actually it's a just like a ring, okay, just like a ring, because this is the circular bar, so this is just like as a ring, okay, for this bar, because you are taking one section, it means this section will be around the bar, it becomes like ring, okay. So from this section, this side, from this end, you can say this is A and this is B. So from end A side, at x distance, this strip whatever you are taking, the thickness of this strip is nothing but dx. What is this? Dx. Okay, dx. It will help you out for the calculation later on. Dx. All right, at distance x it is available, and if you go and check the width, okay, so that you can take B. All right, now coming to the one by one, now we'll go. Consider an element length of bar dx at distance x. We have taken this one element, as I told you, this element is just like a ring, okay, from a larger end, which is nothing but A. The diameter of the bar at this section is. How to calculate this value? So it's very simple. In simple mathematics also you might have seen the value of this bar is nothing but, see here, this diameter at this distance x, the diameter will be d is equal to, d is what, at distance x, I must say d diameter at distance x means for this I'm saying, for this element where I have taken this diameter dx will be what, it is d, I must write capital because everywhere diameter I have taken capital. So dx, and remember this diameter d at point x, that's the mean of it. So what will be the diameter? This diameter will be, you check, this is nothing but d1 minus, okay, I'll show you and I will prove also, d1 minus d2 by L, okay, into x. Again I will write, see, I will write and I will show you dx, that is the diameter at point x. You can write diameter of bar at point x, okay. So this dx is nothing but what you have written, d1 minus d2 by L into x. This is the, just write your formula you have written. How you made formula? Actually, there is the mathematical techniques also available behind this, but don't go in that. I will prove you this is right or wrong. I can write diameter at point A. Diameter at point A. Point A means at this end. Huh? Check at this end diameter d1 minus d2 divided by L. What will be the x value? What will be the x value at point A? Because x you are measuring from this point A. So at point, exactly at point A, what is the x? It is 0. It is 0. So ultimately diameter at end is nothing but d1. Now similarly you can find diameter at point B. So minus d1 minus d2 divide by L, and put x value at point B. What is the x? At point B, x becomes L. If you check d1 minus L cancel out, it will be d1 minus minus plus d2. So this value again it is cancel out, you got here d2. So ultimately at point B, what is the diameter? It is d2. At point A, what is the diameter? It is d1. So like whatever the mathematical formula you have created here, uh, this one is what satisfied to this bar. It is very clear now. So what you are going to do at exactly at distance x, what is the diameter? You have calculated dx, and this dx once you got, this is the diameter at point x, then you can calculate the area also at distance x. What is the area? Area at distance x. What is the area at distance x? It is ax. What is the formula? Because it's a circular bar, so pi by 4, diameter at x is nothing but dx. Pi by 4 dx square. Now you got this pi by 4. What is the dx? Dx you have now d1 minus. D1 minus. You can consider this d1 minus d2 by L. Any constant you can take. Okay. Any constant you can take. Because d1 is constant, d2 is constant, so L is constant, you can take C for constant. Okay, C for constant. So now you can write d1 minus C, d1 minus Cx. Remember value of C. This is square. This is square now. Okay. Now if you want to calculate what is the extension or change in length, change in length. What is the change in length? If you know, remind the formula. So change in length is nothing but it was given delta L. What is the formula? PL divided by AE. Simple. This was the formula, right? Now you are calculating for change in length for this small strip. What is the strip? Elemental strip dx. For this you are going to calculate change in length. So if you go for the change in length, delta L, for x you are calculating, because this small strip you have taken and you are calculating everything like change in diameter and change in length you are going to calculate for this small strip dx, and then you will integrate this from 0 to L, then you will get for the complete bore. That is your actually idea behind this calculation. So for the small strip dx, you are going to calculate change in length. So it becomes delta Lx. Now obviously delta Lx you are writing. So this P and this L will be small strip length dx divided by area will be for the small strip x ax, and this is E. Now all value you keep here. So P dx divided by ax is nothing but just now here you have written pi by 4 in bracket d1 cx square, and obviously then capital E, that is the Young model. Delta Lx you have calculated. If I say what is the change in length, I can write here change in length, change in length for complete bar. Because whatever the change in length you have written here, this is for small element. And what was the element? It was dx element, right? Now if you are going to calculate change in length for the complete bar, then what you will do, that you value you have to write delta L, and how you will calculate, you just integrate from 0 to L to what? To this delta Lx. If this delta Lx you integrate from 0 to L, then you will get the change in length for complete bar. That is your job only. This is the done now. I will write the another step also. Hope this one is clear. Now coming to delta L for the complete entire bar, the change in length will be 0 to L. 0 to L. T is nothing but as usual load. Tx you can write, and area pi by 4, it is nothing but pi by 4 d1 minus cx square into Young modulus E. Now just simplify this. So what you will get, it's nothing but 4p divided by pi. You can take outside this 0 to L, and pi E also, Young modulus also take. What you will get, dx d1 minus cx square. This value you will get inside the bracket. Okay, it's very simple. Now if you integrate this, then what you will get, 4p divided by pi E, and this C constant will come outside once you integrate. Okay, and in bracket what you will get, simple, after integration you will get 1 minus d 1 minus cx, put the limit 0 to L. This constant only come this side only. Okay, here after integration you keep the limit. So after keeping the limit, what you will get, delta L is nothing but the constant you can take here, how much, 4 p pi ec, and in bracket if you keep this value, I mean if you keep the limit, so what you will get, 1 minus, check, instead of x you have to keep L, and second time you have to keep 0. So what value you will get, C, what value you will get, 1 minus d1 minus C L, 1 minus d1 minus C into x value will be 0, right? This will be the value. You are keeping limit for the x only 0 to L, so you kept here, check, it is nothing but 4 p pi e. What is the C value? If you remember, it was d1 minus, sorry, what is the C value? Let me remind. C is nothing but d1 minus d2 by L. d1 minus d2 by L. This is what C, right? And here 1 minus d1 minus C value is nothing but d1 minus d2 by L minus 1 minus d1, because second term will be 0. Okay. Check here. You can take this L upside also. So 4 pi L divided by pi E. Here it is d1 minus d2. Okay, in bracket 1 upon d1, L here cancel out, see this L and this L cancel out, so 1 d1 minus d1 minus minus plus d2. Okay, minus 1 upon d1. Now check d1 again, here it is cancel out, so what you will have, you will have delta L is equal to 4 pi 4 pi L pi E d1 minus d2, in bracket what you will have, see, you will have 1 by d2 minus 1 by d1. All right, now coming to this 4 pi L pi E d1 minus d2, take LCM here, what you will get, d1 minus d2 divided by d1 into d2. Again this part, I mean the whole part, if you keep this bracket value here, so you can check this and this will be cancel out. So what you will get, see here, what you will get, change in length is nothing but 4 pi L, you will have a pi E d1 into d2. This is the final change in length value for the tapered bar. Now access point of this, see what is the access point, or we can say for for simple bar, simple bar if I say means it's a d1 is equal to d2, means simple bar means both side diameter is what, same, means d1 is equal to d2. Now this is d1 and d2 but both are same, then what will be the formula here? If you check what is the change in length, it was PL divided by AE. If you check PL, what is the A? Pi by 4 d square E, that is 4 PL divided by pi E d square. Now check our this formula, this is right or wrong, how you will get, Now if it is a simple bar, so what is the change in length? Delta L is equal to, you are having 4PL in derived formula pi E. What is the formula you have derived? D1 D2. See, D1 D2. But as you have seen D1 is equal to D2, then what will be the formula? 4PL divided by pi E. D1 is equal to D2 means D square. See, the both are correct. I mean, both are matching. It means what you have derived, this formula is correct only. That's the mean of it. All right.